Hi everyone. Today I am going to talk about distributed computing. I've done some videos around cloud computing, and distributed computing is actually one of the key thing because of which cloud computing has been enabled and currently is so widely in use. So it's like one of the core pillars of cloud computing is distributed computing in itself. Uh, and like always, what I would try to do here is I will try to uh, provide you guys intuition around what exactly we are trying to achieve with distributed computing, and when we start dealing with distributed computing, what benefits it gets, but at the same time what challenges it exposes. And then maybe we'll start dwelling into, if not in this video then in subsequent videos, some architectures patterns around solving those challenges while trying to achieve the benefits that we aim to get from distributed computing. Okay, so let's move on to a real world example that we can use uh, for intuition on distributed computing. I was thinking about various examples and this one came to my mind. So imagine there is a food van. So, let's say in your university campus or somewhere, you want to go and grab your lunch. So there is some food van, and the goal here is to try and understand how that persons or person running food van, how they can optimize the way they serve their customers, right? So there will be a lot of people trying to order the food, let's say burger or whatever, take away from that food van. So how in the food van that can be optimized? So initially there will be a bunch of people, and then obviously you would like to serve them. So obviously the most important thing is you'll assume that they will come to that food van in some form of queue, right? So that you can start serving them in an order. And the idea here is to be able to serve the customers and at the same time being fair to everybody who wants to purchase food and get served through it. So okay, so that's good. But let's say this food when it starts becoming popular, and then more and more people are uh, queuing up. So when more and more people start going up, what do you do? How do you ensure that you still achieve the customer satisfaction? You make sure that people get served in enough time and all that. So, I mean, one approach could be you probably have something where you start putting, like multiple stoves, burners inside, or something that allows you to increase your capacity. So by that, what I mean is you probably would like to have a way by which if you are preparing in 1 minute one burger or one takeaway, you can start doing it in a way so that you can prepare maybe 2 in 1 minutes, or something like that, or maybe 3 in 2 minutes, something like that. So you probably would like to do that by adding more capacity to your food van, and that could be something on the lines of maybe multiple burners in there, or some other way by which you could have two burners in there or something like that. But then you are basically kind of doing all that in that food van. So basically what I'm trying to show here is now you've kind of grown slightly. And actually that is one form of what we call scalability in software development, and that is called vertical scaling up. So I mean, and maybe this is a very relevant example, or maybe this is not that too relevant. But the idea here is, yeah, while being in that same, let's say, server or computer, when we talk about programming or resources, computing resources, etc., you can what we call vertically scale up. You can add more computing resources, you can add more CPU, more RAM, more if you want to store more data, more hard disk, those kind of things. So that is one form of it. So yeah, the idea here was trying to say that okay, maybe you will try to instead of having a burner with or the four grill burner, two grill burner, you will have four grill burner and things like that. So you probably will try to do something on those lines while using the single food van, and that way you will try to serve your customers. But then eventually it will come to a point where it is no longer practically feasible. So you cannot serve all those customers with just one food van. So what you will do then next? So obviously your business is expanding, more and more people want to use it. So maybe as an owner of that business, you say that, okay, I want two food vans. So the idea there is to be able to serve again more people. So you want to have better performance in that sense, right? So this is again analogous to another form of scaling up in what we call horizontal scaling in software development, and that's where we start getting into basically distributed computing and things like that. So the benefits that we get, the challenges that it starts with, we will start talking about all that with this practical example. So what we are saying here is by horizontal scalability, what we are saying is now we have had enough of trying to serve as many customer as we can from a single food van. So now we are trying to add another food van, and then we'll try to see how we can serve our customers through that. So let's dwell into that. Okay, now let's start going into the nitty-gritties of logistics of how you would serve lots of customers through this approach, where instead of just one food van you have got two food vans. So okay, we earlier talked about, okay, there will be a queue. So now the first obvious things that comes to your mind is, yeah, let's make two queues. So one for food van number one, another queue for food van number two, and then people will of course approach to that queue through that queue to that food van, and then they will say what their order is, they will tell what they want, and then they will pay, and then they will wait until their order is fulfilled and eventually take their order. So this is what is processing happening here. So somebody is taking their order, telling them how much it will cost, taking money from that, and then letting that person who is actually the chef or cook know that, yes, now you have to make a veg burger for this person, or another one has ordered, let's say, non-veg chicken burger, then you probably will say something like that for that person. You are taking orders, and then you are letting the cook know what those orders are, and then cook is trying to serve those orders. So that is what is happening in both. Now you could very easily, you could see that this, and you, most of us who have been in parallel queues on in supermarkets still, etc., we must have observed this, right? So you are standing in one queue, very quickly you might say that, okay, the other queue is going faster. So it could be for various reasons, maybe the people are working at different pace or something like that. So now you want to, while you are trying to serve all the customers in a proper way, in most efficient way, but you might find that having individual queues for each food van is not good enough or is not most performance enough. So that's where we start talking about challenges of distributed computing and how you can start solving it. So first of all, let's start using our analogy to start, bringing in some key terminology terms in here. So first of all, when we said that we will have two food vans, what we are saying here, we have, in terms of distributed computing, you can start thinking of, we have a distributed system where, and in this distributed system we have, let's call it processing nodes or worker nodes. So we have two worker nodes in here, and we have created two worker nodes by horizontally scaling out. So we have got this idea in mind that if in this system, if my business expands, I can add a third worker node, I can add third food van and all that. But then very quickly we realized that just adding them in a way so that they are totally independent of each other, with each one getting their own queue of customers that this node, this processing unit, this, let's say, servicing unit, this has to serve, that may not be very efficient. So immediately we start thinking that, okay, some form of interaction is needed or coordination is needed so that this distributed system, which is consisting of more than one processing units, more than one nodes, in this example, more than one food trucks, it could be as efficient as it can. So then you start thinking about how to do that. So, and for that, uh, I think the very obvious thing that might come to mind is, okay, what we will do is we'll have some kind of, like a queue manager here, or queue, or a guard kind of person. And what it will do is, instead of having one queue each dedicated to every food truck, in this case, we could have somebody who will look at how many people are in the total people, or start looking at that queue, and then that person needs to have some knowledge of uh, which food truck I need to send them to, so that people are not waiting too long, and if they are in different queues, then those queues are not being in one way or other unfair to them. So this person now needs to coordinate in some way how we are using the resources in this processing units in these food trucks, and then use that knowledge to start diverting people from this queue to the right food truck. So what I mean by that is, if you think about it, or even before that, let's take, so basically the idea here, what this person is trying to do. So let's again use our analogy to understand again one of the important term used in distributed computing, and that is what is called load balancing. So what we are saying here is there is a load of lots of customers who want to be served, and what this person is trying to do, or this guard, or this coordinator is trying to do. Many times in distributed computing it is called coordinator, and so, but here what we are trying to say is, in some sense we are using that coordinator very initially in a very rude way to just distribute the load. So this guy could use a simple, in our terminology we can say an algorithm. You can say that, okay, I'm going to send this person to this truck, and then second person to this truck. So first one comes in, goes to truck number one, second one to truck number. So basically I'm kind of flipping, alternating each truck. So that is like one of the important algorithm as well. We normally call it round robin algorithm. So first person, okay, I'm going to send you to truck number one, for truck number one. Second person, I'm going to send you to truck number two, then third to one, then four to two, and so on and so forth. So this is like a very simplest of simple, you can even say load balancing algorithm, where you are diverting these people to the right processing, to one of the processing units, and then let them be served by that processing units. But then there could be problem in that as well. If you start thinking about the actual way these people will be served by these food trucks, you can again start uh, finding out that there could be kind of inefficiencies in that approach as well. So what could it be? So you took person number one to food truck number one. That person has given an order. The person taking order from the food truck told him or her, okay, how much is your money that you have to pay for this order? He paid the money. Now the person who was taking order, he or she has now passed on the order or the information that contained, the person number one has ordered a veg burger. That information is now passed to the cook. Now cook is trying to look at that information and now start preparing that veg burger. And then while the cook is preparing the veg burger, the person taking order is now taking order from the second person who might have said, okay, I want chicken burger or something like that. So on and so forth. So that process is now happening on that food truck. And now that process, so depending upon what ingredients here are, maybe, so it is taking longer to do the chicken burger rather than to do veg burger, and so on and so forth. So what you could very quickly end up in is this queue might not be of the same size as this queue. So now if you immediately start sending people in just what I call round robin fashion to these trucks, now you can start appreciating that that approach is not very, let's call it fair, or is not most efficient. So you need to have some more control over it. So now what could be the easiest way to get that control? So what that could be, that this person, the one actually which is kind of diverting you, it doesn't simply diverts you to the food truck without knowing what the food truck is. It needs to also have a knowledge of, okay, how many people have already given order and are waiting for their order to be completed. So for example, if it turns out that there are 4 people here, and but maybe more than that in here, then obviously it will make sense for this guy to say that, okay, now I'm going to divert this to food truck one, because food truck one had only 3 pending people, and food truck two had 5 or 7 pending people who have already paid and their order and waiting for their order. So again, I'm not going to come up with all the possible scenarios here, but the idea of doing all these talks was to try to tell you guys that, okay, as soon as you start putting distributed computing, first of all, why we are doing distributed computing. So start taking this analogy, or even start going into, some kind of, let's call it, terminology, etc. So what exactly is distributed computing? So distributed computing is something where we are taking multiple, let's call it, processing units, or in very simple terms, multiple computers, and then we are trying to combine them together to solve one problem, to come up with a solution for one problem. So uh, we talked about some terminology here. We talked about scalability. So you will try to uh, do that with one computer as much as you can, but then after a certain point, you will not be able to do it just with one computer, and hence you have to add more computers. And then the idea there is, when you try to add more computers, you want those multiple computers to work together, and that is where I was trying to give this analogy of trying to introduce a guard or a person who is kind of looking at the queue, understanding where to send that person to which truck, and so on. So these three things together, uh, or all this coordination together. So first of all, what are the distributed? So there are two terms in here: distributed systems. So yeah, you have multiple computers, then you have some way by which you can distribute the load on those computers, and then normally, you have some what we call load balancers, etc. for that, pertaining on to different algorithms. So they are parts of what we call distributed system. So then there are multiple parts of that distributed system, and when these parts work together to solve a problem, collectively solve a problem, then that is what is called a distributed computing. And now we will go into some. So I'm gonna start again, taking this as, some kind of, let's now go into theories and some terminology and some definitions that might be beneficial for you with that analogy, that example. So here I've put in some definitions from some well-known websites. So I think again I took it from AWS and things like that, where they were trying to explain it from the context of cloud computing or something that helps cloud computing, etc. But end of the day, what they're saying, so we are taking multiple computers. In our example, there were multiple food vans trying to solve a problem. And then there are certain, what I would like to do is, there are certain key topics or key concepts here that I would like to introduce. Again, giving example of our food truck. And then these are the terms that you'll hear when you will talk about distributed computing. So I'll try to kind of introduce you with these terms, and then in the following sessions, we'll start dwelling into details of each and everything. So first of all, performance. Yeah. So I mean, this is kind of obvious. What we are trying to say here is we want to serve as many customers as possible. So we want to increase our performance. So when we want to serve more people, and we cannot do it with the limited, if we have only food truck, then we will reach a limit. So we want to fulfill the needs of all the customers or more customers, and for that we will have to add more machines, more resources, more computing resources, and hence distributed computing will end up achieving more performance. Then scalability. This is a very important. Again, I would say that this is something that is used very often. So what exactly it means? We are scaling out, and by that what we are trying to say is, how do you, if you want to achieve more performance, if you want to serve more people, let's say, let's stick to our analogy here, then how do you achieve it? So one way was, we talked about that you could add more burners into that food truck, but then eventually you will reach a point where you'll say that, okay, I want to add more. So in this example, I'm showing two food trucks, but let's say if it was something where you have kind of developed a system where you could easily keep on adding more trucks, and then keep on adding them in a way so that this whole system starts to be able to serve. You have kind of a way or process by which this whole system, whether you have two trucks in there or 20 trucks in there, is kind of agnostic to that, doesn't cares about that. You have come up with a process. So the process could be, okay, if I go back to my round robin example, okay, there is just one guy here. He says, okay, I'm gonna take person number one, put him to food truck number one, then two to food truck number two, and so, and I'll keep on round robin between them. In that example, when you add food truck three, he will then round robin between one to three, and after three he will go back to one, and then if there are food truck number four, he will go from one to three to four, and then after four he will go back to one. So that thing, so basically the act of adding a node is not changing. Act of adding another food truck is not changing anything. The whole system is working as it is. The guy picks somebody from here, assigns it to one food truck, then another one assigns to another food truck, and so on and so forth, in kind of like a fixed manner. So that algorithm is still working. So when we say scalability, what we are saying is whatever you are doing, it's easy to add more processing units. It's easy to, so when we say horizontal scalability, we are saying that it's easy to add more processing units. It's easy to add more units which are actually doing your work in a typical scenario. That is what is called a horizontally scale out cluster. So there are lots and lots of open source technology, and in fact my idea of giving this talk was to introduce these basic concepts to you guys first, and then we can start building some framework where we will discuss all this, is we call it scalable technologies. Like I'll give you a lot of examples here, but some of the key ones, people who are actually from this field would know it very well. There is Cassandra, which is a NoSQL database. Then there are messaging systems or event processing systems, for example, event streaming systems like Kafka, etc. They are, or search engines like Elasticsearch. They are all called horizontally scalable systems. So the idea there is that when they consist of, again, a distributed system. Normally it is called cluster, which has got multiple nodes, processing units. And then the idea there is whatever algorithm with which these things work and they fulfill the requests that are there to fulfill, when you add more nodes to that system, everything keeps working. So everything keeps working, like in my round robin example, whether there are 2 food trucks or 5 food trucks or 10 food trucks, right? Nothing needs to change. This guy only needs to know that, yes, there are more, how many total there are, and he will keep on doing it in a round robin fashion. So that is what is called horizontal scalability. And then we talked about 2 types of scalability. So that is what is called horizontal scalability. Now let's talk about availability. This is a very important, again, concept of distributed system. So one of the benefit of distributed system, performance, but then another benefit of that distributed system is availability. So again, go back to the system. If for whatever reason, let's say, I don't know, I mean, let's say that burner in this food truck for some reason is having issues, something went wrong. Now at least it's not like all your customers are not getting served at all. Now this guy, as long as this guy knows, this is actually very important. I have just said it few words, as long as this guy knows. So yeah, this guy should know that the burner has gone out of order for some time. So then what this guy can do is start diverting people to just this food truck. Or if there were 3, then start diverting these people to 2 and second and third food truck, and take food truck number 1 out of equation for some time. And as soon as this guy knows that food truck 1's burner is now okay, it can resume that whole thing. Now that what it means is, people here, the queue will be served slightly longer. The total time that customers will be served will slightly increase, because now instead of 2 in this example, let's say there is only 1 food truck, but at least the whole thing will not fall apart. It's not like for certain period people are not being served at all. And that is again one of the important concepts in distributed computing, and is applied in all forms of distributed computing, and is one of the important tenets of the what we call nowadays cloud native applications, which are built on a distributed architecture and all. So what is it is availability. So there is some availability. So if one part of the system dies, the rest of the system continues to work. So that is what we are trying to do here. So if a burner in that, or the guy who was actually taking the order for whatever reason, I mean, that guy has gone for a short loop break or some break or something, at least this guy should know. As long as this guy knows that, we can handle those types of problems. So that is what is availability, and there is, again, I would like to point out that there is a term called always on. So in many days, I mean, sometimes it feels like a catchy term, but yeah, that is the whole idea of availability. Nowadays, in a global market where you may have your customers all over the world in different geographies and all, it starts becoming important because then the customers might be coming to your website all the time. So designing your system in a way so that it is always available, and for that to become always available, you have to use these tenets of distributed computing. So that is one thing. Okay, so now moving on. Yeah, I've said here fault tolerance. Again, this is again a term which has sometimes being overused, and sometimes people kind of just overdo it. But the whole idea here is, so one of the way by which you can achieve availability is fault tolerance. So if anything goes wrong, you have a way to handle it, and how you will handle it. So for that, let's start looking at two rest of the two. So these two terminologies, redundancy and replication. So yeah, so kind of related to what I've already discussed about availability, but yeah, how it is achieved. So some form of redundancy and some form of replication. So now let's start going back to our example of food trucks. So as I said, okay, let's think about, on at least on a very high level, what is redundancy. So um, uh, you could in theory say that. So I'm just thinking an example, a better example, rather than saying that yeah, there are two food trucks, so actually at least one is redundant. In some way it is redundant, that might also be true, but in other ways it is not really redundant, because you kind of know that if there aren't enough food trucks, I won't be able to serve my customers in time. So from that reasoning, it's not purely redundant, it's like an important part. But yeah, you will only tolerate that what we call reduced performance when there is a problem. But if we take another example, let's take an example of how you would do it. So let's say that the person who is taking an order, and I'm thinking of this example because I want to introduce you guys with these two key concepts, redundance and replication as well. So we kind of said that yeah, if one of the food, if there is an issue with one of the burner, at least second is there, so you can still keep on working, uh, even though with a reduced performance, but you can keep on working as long as these guys completely, you can divert those people to there, so everybody's served, but maybe with a longer period. uh, then what is replication? So redundancy is just saying that you have at least an extra resource or node to complete the task. Main node that was responsible for doing the task is not available. So in this example, we are saying that, okay, as long as this guy knows, yeah, they can divert and here. But let's look at another thing which is called replication. And sometimes people get confused between redundancy versus replication and all those things. So replication is basically, what we are saying here is, if we have a mechanism by which we have additional copies of information needed to complete the work, then through replication we can achieve high availability, or by virtue of replication we can continue to serve our customers, or continue to complete the work, continue to keep on doing the work, and not go into what is normally called downtime. So let's elaborate that slightly. So what we are saying here is, um, let's say that this person, when we are in this sub queue, and this person has given an order. So the person taking the order has taken the order and put that, let's say, information which says that this first person wants chicken burger, and then the second person wants veg burger. That information has been stored here for the cook to start working on it, but cook has not yet reached working on it. But the person taking the order has taken the order, has taken payments from these two guys. Now, at that point, the burner fails. So what do you do? Right? So you have already taken money from these two people. You've taken the order. You have taken the information around what uh, uh, their order is, taken the money from them, but their order has not been fulfilled. So do you want them to wait till the burner is back, or maybe the burner may not be back for the whole day on this food truck? So how do you do that? So that is where I think, and again, I'm trying to draw this analogy. This may not be, again, I would say, perfect example, but at least for newcomers, it might help them to start thinking in terms of replication. So what could be done is, this guy who's taking the order, as soon as it takes the order through maybe telephone or something, or it tells the guy who is here also taking the order to say that, okay, so basically they have like a central place, yeah, and that's where maybe a centralized database, but then again with high availability and all that might come in. But the point is that information which is available only to the guy taking order here, if somehow that information is shared to this guy as well with some additional information, I am taking order, my order is fulfilled, I am taking order, my order is fulfilled. If these two guys start sharing this information with each other, either by putting it in a central place or somewhere, then I think the problem starts getting solved there as well. So because then that could be that, okay, I am taking order, and it could be something like, okay, this person is solely responsible for serving these customers, but before they take any more from this queue, and with the coordination of this guy, they can somehow do it in a way so that if the burner blows up here, the pending orders from here are served here before new guys are coming and giving their order and making the payment. So now you can start thinking that while we have achieved high performance by adding more food trucks, if we really want to do it in the most efficient and fairest way, then there are some challenges, and those challenges can only be solved by exchanging some information, by keeping multiple copies of that information, replicating that information. So here I said you can replicate it, you can put it into some central place where you will know that, okay, there are some pending orders, and then this guy before taking more people in there will say that, okay, are there pending which have not been served, and rather than this pending remaining pending, it will, instead of taking one more person, that pending can be moved to this guy, and then this guy can serve it. So the point here is that needs additional information to be stored, or that needs that information to be copied so that that information can be acted by someone else as well to complete the work, and that is what is called replication. So you are creating more copies, so that that additional information, I mean, yeah, it's not, many a times this replication is there to handle if the data is lost, so like if the information is altogether lost from here. But yeah, the loss could be because you have stored that information here, and end of the day, whatever act was to be done on top of that information to complete the work related to that has not been done, so we still need to act it. So all those things are important. So what is redundancy? Let's look at just this line. So have an extra node resource to complete work in case the main one doing work is no longer available. So I think this is kind of like obvious in what we are showing here. So if there is any issue with, let's say, one of the food truck, at least there is another one to serve it. Although now what it will mean is your performance will slightly reduce. You will be not able to serve the same number of customers per minute, or you say per unit of time like you were doing earlier, but still you will keep on working. It's not like everything will go down, right? So that is redundancy. So you have some redundancies in this system by having multiple food trucks. And then there is another thing, replication. So replication is what it says here, have additional copies of the information needed to complete work. So let's think of a scenario here. So the person taking order has taken order here. Let's say it has taken order from 4 people, and while the cook is working on the order of the first person and 3 more are still pending, let's say something went wrong, and again the burner went wrong. Uh, so what do you do there? Do you the remaining 3 people are never served there while this guy keeps on diverting people to here? Uh, Not really. So what we could do is, I mean, a simple solution could be that the information about how many orders have been taken and not served may somehow be passed to, let's say, maybe this person, right? And then what this person can do is this person will say, okay, before I invite another person to go to this, as soon as I know that the burner is gone wrong here, and I also know that there are three more person waiting in here, I will, instead of taking more orders here, I will have that information that was replicated to me, that was passed to me, maybe somehow communicated to this person. So yeah, those kind of things can be done. But then or you could have some other, I mean, I would encourage you guys to think of some other solutions as well. But the point is either via this coordinator or by directly coordinating between these two guys. So the people who are taking order, they can directly coordinate between them, and then this order taker will know the pending orders from food truck number two, and the one in food truck number one or food truck number two will know the pending orders from food truck number one, and so on and so forth. And then using that replicated information, then they can be more fairer to people who are waiting for their order to be served and have already paid for. So basically what we are trying to say here is, by using redundancy, by using replication of information, by creating additional copies of information, you can achieve availability. Replication is, I mean, we'll talk about if we get to that point, depending upon how much interest there is in all those things. When we go to, things like SQL, sorry, this NoSQL databases, Cassandra, etc., they have their own ways of replicating the data. Kafka has its own ways of replicating messages. Elasticsearch has its own way of making replica copies and all those things. So the idea there is multiple copies are created, and one of the purpose is if one of the copy is lost, then at least you have the second copy. But if you think about why you have the second copy, so that maybe you are either needing that information forever. For example, it could be in the database and you need it for the long term, so you still want an additional copy in case the main copy is gone, or you want to act on that information. Either way, you are creating replica copies so that whatever the intention is to do the work, that is can be served. So that is what is redundancy and replication. Transparency. When I was reading about, what are the very value propositions, one of these things came in. So I will just quickly mention it. Transparency, what we are trying to say here, the whole system should be presented to the end user. So the multiple things that constitute your distributed system, they should be presented to the user as a whole. So the point being that you as a person standing in the queue, you shouldn't really be caring about whether there are 2 food trucks or 20 food trucks and so on and so forth. So for you, you have to deal with this person, and then there is a process. It will be diverted to eventually one food truck. And when more are added, or when some of the food trucks go down, there is a problem. You as somebody standing in this queue, you shouldn't really be worrying about it. So for you, how many food trucks are there, etc., and all those things is kind of transparent. You don't know about it. So this is like so I would finish this talk by introducing another important point that is always considered in distributed systems. I will write it down here. Avoid single point of failure. It is normally acronymed as SPOF, single point of failure. And what exactly we mean by that, I think some of you might have already identified that. But yeah, if you look at our final system that we talked so far, this guy here, this guy is our single point of failure, right? Because if for whatever reason this guy is not able to do his work, maybe he is needing a short break, or has gone for loo break or whatever, in that time, now we are back to square one. The whole chaos may happen, because now whatever we were trying to do by having a process through which these people can be served in a fair order among all the food trucks that we have. Now that process, this guy was coordinating it. So if he's gone, the whole thing is back to square one. So in any distributed system, we always want to avoid single point of failure. So we need to have something in here so that there is again redundancy for even this guy. So yeah, there are multiple ways for that, and I know this talk is already getting very long, and I wanted to just do the intuition. So I'm going to leave you guys with just that thought that yes, single point of failure should be avoided in all the distributed systems, because that is very key to having high availability. And yeah, Hopefully, you guys have found this talk interesting. And as always, if you have any questions, leave them as a comment. And yeah, I'll try to get back to you with answers. And based on the interest, we'll do more follow-up sessions. Thank you, everyone.